Okay, so good morning. Welcome to this third day, which is dedicated to dynamical systems. And we will start with stability analysis by Professor Smith.
Better? Can you hear me? It definitely reverberates in here. Okay? Yeah, okay, up there. Good. Okay, so we talk about stability analysis, and I'm going to give you, let's say, a quick rundown or an overview of the tools of stability. And I deliberately threw in that modern, that adjective modern. It's a little bit daring because it could be not modern, a year from now. But nevertheless, I'm trying to somehow connect what you might know from a fluids course or a hydrodynamic stability course and connect that one to the complexity of things that we have to actually deal with in terms of stability theory. Okay, but to start out with, let me just give you a little bit of a motivation before I hit you with some equations. So fluid instabilities, stability theory is a central discipline of fluid mechanics. Just open JFM, and so there's always a stability analysis somewhere in every issue. So fluid instabilities are all around us. Everywhere you look, you can see a fluid instability. They appear on all spatial and temporal scales. Okay, from the small one, microfluidics, all the way to the atmospheric sciences and oceanography or astrophysical applications. And they're caused by a multitude of phenomena. Okay, I'm going to show you a few examples on the next slides. And they also have a great impact on technologies and environment. We do have to care about instabilities because they really limit an operational range of a fluid device or some, they are responsible for safety margins of certain devices and so on. Okay, so here are just a bunch of examples of fluid instabilities, and I'm going to write down what sort of the main component of that one is. So the most common ones are probably shear-induced instabilities. So we have the UDY, which causes positive feedback in the flow that creates some patterns. For example, that Kelvin-Helmholtz instability of that lenticular cloud hanging over a mountain. A little bit more from a simulation. This is the Rayleigh shear instabilities of a rotating disk. We're sitting on an instability as we speak. So this is a thermally driven instability of the core mantle, the Earth mantle convection. Okay, so this is a instability going on all the time in the core of the Earth. So this would be the same one for a laboratory experiment. Rayleigh-Benard convection, a very famous one with the hexagonal patterns. That's an instability that is thermally induced. Okay, interfacial instability is the breakup, very classical one, of a capillary jet into little drops. That one can be written as an instability of a columnar jet. Okay, and then you can push that one quite far. Two colliding jets make this fishbone instability that is also interfacial in nature. Okay. Free surface instabilities, this is a capillary wave propagation. That one is an instability on the free surface waves. And you can even go to non-traditional fluid applications and do the sand dune ripple formation and describe that one as an instability on the sand dune. Okay. Then we also have magnetically driven instability. In that case, the magnetic field is the main player in that instability. So this is a ferrofluid which has surface instabilities. You put a magnet underneath. It's very popular in science museums for kids to play with. But on a more larger scale, this is a MHD instability of a tokamak plasma. Okay, and then actually these instabilities, there's plenty of them, and they're very, very tough to control. The instabilities, the magnetically induced instabilities in that MHD tokamak plasma is probably the main reason why we do not have nuclear fusion at the moment. Okay, just getting those in check is the main challenge, among many others, but it's one of the main challenges. Okay. This is a buoyancy-driven instability. This is lock exchange flow. You have two different fluids. The heavy one goes underneath the light one and then creates these Holmboe instabilities. for a lock exchange flow. And you can also scale that one up from a lab experiment. This is a picture of Lake Geneva, and there's a buoyancy instability there that is responsible for nutrient transport in Lake Geneva. If you go really high up in Reynolds numbers, then you can also have rotationally driven instabilities. The spiral galaxy and accretion disks are just full of instabilities. The spiral arms that are forming are manifestations of a rotational instability. And for example, the red spot on Jupiter is certain an instability. Also, morphological instabilities, that's not what we really think about an instability, but if you have a gradient in some kind of a chemical concentration, in that case it's calcium, you got actually the formation of stalagmites and stalactites in caves is a very slow instability, but nevertheless it's a morphological instability. Okay? Same thing goes for the thing that's called penitentes. These are ice sculptures, so to speak, in the Andes. They're about 2 meters high. You can walk in between them if you dare to do so. And that's a radiative sublimation instability that actually forms the penitentes and sets the scales in the spatial directions. And finally, combustion instability. In that case, of course, it's reactive flow. You have all kind of instabilities on that one. All right, so before we talk about stability, let me also introduce the stability concepts, because stability has been around for a long time. It has been treated mathematically, not just by the fluid dynamicists. So what do we usually understand, or how do we define stability? Okay. So the definition of stability is usually given in a context of a dynamical system. We have x dot is equal to f of x, f is nonlinear, and then we have some kind of an equilibrium point. That could be an exact equilibrium point or a quasi-equilibrium point. Okay? And then we're going to follow a small perturbation about this equilibrium state. So we're going to zoom in onto this equilibrium state and see what happens if we deviate just a little bit from it. And then the classical pictures in all the physics textbooks is like this. Okay? So we have a ball like this. You displace it here. The bottom is an equilibrium point. If you displace that one, it rolls down the ball and returns to its equilibrium. It's stable. If it's unstable, it rolls off and it's indifferent or neutrally stable if you can just push it back and forth and it stays there. Okay? So this is a little bit of an intuitive way of describing the stability of an equilibrium point. The person that somehow first mathematized the whole concept is Lyapunov. Okay? He also started out with a dynamical system. X dot is f of x of t with an equilibrium point, just like before. And then he wrote a paper in 1892 that suggested two stability concepts. Okay? So there's Lyapunov 1 and there's Lyapunov 2, both in the same paper. And Lyapunov 1, this is the mathematical definition, says if we start out somewhere a delta away from the equilibrium point, we're going to stay in an epsilon for all times. Okay, that's the definition of stability. We're not moving away. We could move away, but we're not really shooting off very far. Okay, so you have a delta neighborhood and an epsilon neighborhood. This is where you start out. This is where you end up in the worst possible case. Okay, that one is called Lyapunov stable. The second one is if we return for time to infinity, we return to the equilibrium point eventually. So in that case, that epsilon is going to 0. We're actually returning back. Okay, it's a special case. Then we're saying we're asymptotically stable. Okay, and that paper actually had quite an impact because it first formalized a stability concept on which you can actually build all kind of mathematical theories. Okay, but you should notice one thing in both definitions. Okay, this is for all t, and this is t to infinity. Okay, so for all t and t to infinity basically means there's no time scale in the stability definition. Okay, as long as this thing eventually returns back to the equilibrium state, we're going to consider it stable. Otherwise, it's unstable. Okay. So then, of course, this got picked up immediately. You know, it was a very successful paper. Nowadays, you would say it's highly cited. Okay? And it was translated for fluid systems. Okay? So we have a equilibrium state. That would be our base flow. Okay? That's our equilibrium state. And then we're gonna have a small perturbation around that one. So we go an epsilon away. And we just look at the dynamics of the perturbations Q. Okay? And for small epsilon, they're governed by the Jacobian. And the Jacobian are our linearized Navier-Stokes equations. If you want to modify them, you can actually bring them into a nicer form, and then they're known as the Orr-Sommerfeld equations. Okay? So you have an evolution equation for the with the Jacobian as the system matrix. And then if you throw in the Lyapunov stability concept, okay, that one is equivalent to saying, you know, I'm going to have e to the minus I omega t because I have exponential instabilities. Okay, and then the whole thing turns into an eigenvalue problem for the stability of the system. Okay, here's the eigenvalue problem. The ddt turns into an I omega. That's an eigenvalue problem. And then you just look at the imaginary part of omega here. That makes it either exponentially grow or exponentially decay. Okay. So the eigenvalues of L are what tells you the stability. And that's exactly what we always do when we linearize a dynamical system. Okay. Now, if you do that one, if you form your linearized Navier-Stokes equations and look at the eigenvalues, the largest growth, let's just say a simple flow like Janel flow, okay? And then you crank up the Reynolds number as high as you can. Eventually, this will go stable because it has no inflection point. So there has to be a Reynolds number where you get the maximum growth. Okay? And that Reynolds number is ridiculously high, first of all. It's in the, I believe it's in the 19,000s or something like that. Okay? And if you take the worst possible growth rate you can have there and stick that one in, it's a growth rate that is so small that you have to go 50 channel heights downstream for the amplitude to just double. Okay, so this is about as bad as it can get in the channel flow. Okay, so obviously this is not a very useful tool to analyze channel flow, and the trick for making it a little bit more realistic is we need to somehow reintroduce a time scale. We cannot have that t to infinity or for all time constraint on the stability because most flows that we actually look at don't give a perturbation an infinite time horizon to do what they need to do. Things will change on a much, much faster time scale. Okay? So we have to reintroduce the time scale for a more general and a more realistic stability analysis. All right, so that brings me to the mathematical framework that allows us to do that in the most flexible way that we can imagine. Okay? So for that one, I'm going to take my fluid system, okay? And I'm not going to throw too many equations at you. I just sort of symbolize the equations. Everybody has different equations, incompressible, compressible, multiphase, whatever you have, okay, reactive flows. So this is my fluid system, okay? And I treat it as an input-output system. So that means I somehow define the things I have control over. That's my input. And that could be an initial condition. It could be a forcing from the outside. It could be a roughness distribution. It could be the placement of a bump somewhere. It could be anything that you consider a control variable of the fluid system. Okay. Then it goes through the fluid system. The fluid system does what it does. And then on the output side, I measure something. And that something is just a number, a scalar. Okay? The drag, the dissipation, the Nusselt number, whatever you have. Okay? That's my output. So then, by learning more about the problem, I'm going to say, okay, I want to write this down as an optimization problem. I want to make this output, the drag, for example, as large or as small as I can by playing around with my control variable. Okay? So this turns into an objective definition. So my objective, which is a function of the state and my control, needs to be optimized, minimum or maximum. I don't really care about that. Okay? But I cannot just optimize into the blue. I have to also satisfy my governing equations. Okay, so this is the constraint. I have to be truthful to my Navier-Stokes equations, but within that constraint, I want to do as best as I can. Okay, and that one is a PDE constraint optimization. Now, constraint optimizations are notoriously hard to solve. Okay? What we usually do is we like to have one expression that we optimize rather than saying this is what we optimize, but we also have a second equation that needs to be satisfied. We want to lump the two together, and that one is done by adding our constraint, which is a full equation, okay, with a Lagrange multiplier to combine these two things all together and then optimize it in one shot. Okay? So this is a standard trick to turn a constraint optimization into now an unconstrained optimization, where the constraint is just added with a Lagrange multiplier, and this Q plus is my Lagrange multiplier. That's the one that satisfies the constraint, or makes sure the constraint is taken into account. All right, so now this L, which is known as the augmented Lagrangian, okay, now depends on three variables, the Q, the U, and we introduced another variable, the Q plus. Okay? Three variables, and we have to optimize this expression. Okay? Now, if you have a function with three variables, the way you do that to get the minimum or a maximum, you take the derivative with respect to all three variables and set each one 0. Now, this works exactly the same way here. We take the first derivative, but since we're not taking a derivative with respect to an independent variable, we take it with respect to a function. We have to take variations, okay? But it's the same idea. So I take dl dq plus, dl dq, and dl du. That's my three variables of L, and I set all of them to 0 to satisfy the constraint that this has to be a minimum or a maximum, okay? And just like with functions, you get three expressions for these three conditions. Okay, so here is our Lagrangian. Okay, and now out of this one come three equations. Now, if you have a function, you usually get algebraic equations. Okay? But because we're doing variations, in this case, we actually get equations, not just algebraic expressions. Okay? So the first one is the simplest one. I have to differentiate L up here with respect to Q plus. Well, Q plus only appears here. And if you differentiate with respect to Q plus, it doesn't appear anywhere else, and it happens to be linear. So this whole thing acts just like a coefficient. Okay? So taking the derivative with respect to Q plus is just this coefficient, which is a function all by itself, and sure enough, it's the function that we had in the beginning. So nothing is learned at that moment. This is just bringing back the governing equations and saying, you have to satisfy that. We knew that. Okay? Gets a little bit more complicated for the second one. So now we're doing the dl dq, and we see that q appears here, here as a time derivative, and here inside the f. Okay? So in that case, we have to do a little bit of more work. That one uses integration by parts, but it's not so bad. And then you get an equation that looks like this. Q plus dot df dq h q plus dh dq. So this is the part from differentiating the q in here. That's the h component. That's the f component. And that one is the q plus component from the multiplication of these two terms. Okay? So three terms in that equation. So we see that we get our original evolution equation back, but now we also get an equation for the Lagrange multiplier. That one has its own equation, and that thing is called the adjoint equation. Okay, the adjoint equation, because the Lagrange multipliers are also known as the adjoint variables. Okay. Final derivative we have to take is dl du is equal to 0. Okay. Now, u appears here, twice here in h, and it also is inside the f. Okay. Now, It is not anywhere contributing here. That's the only one that has time derivatives, okay? So no contribution from here. That's why this last equation will not be an evolution equation. It will be an algebraic equation, no time derivative, okay? And this is how it looks like, okay? The h du, which is the part from here, the f du is the part from here multiplied by q plus. That one is the optimality condition. So out of these, satisfying these three things together to get an optimum, we have to satisfy these three equations. Two of them are evolution equations. One we knew, one we knew before, and the other one is a new one that we just derived, and plus one algebraic equation at the end. Okay? Now, strictly speaking, these three equations have to be satisfied simultaneously. Okay? So having this one satisfied simultaneously means we have to solve these three equations all lumped together in one shot. Okay? Nobody does that. Okay? The way we do that is we do it iteratively. Okay? So we say, okay, let's back off on the simplest equation. That's the easy one. That doesn't need to be evolved. That just needs to be evaluated. Okay? That one is going to be, we're going to solve this equation exactly. We're going to solve this equation exactly the way it is, and on the last one, we iterate, okay? So exact, approximate. That's how we do it, okay? And by going around and around in an iterative scheme, we eventually solve the last one also exactly, okay? So here is what we do. We have our governing equations. For the first time in U, we have no idea, we just guess something. If you don't have a good guess, 0 is as good as anything else to start with. Okay, so we solve that equation. Then we solve the second equation, okay, for my adjoint. Okay, so we solve that equation. I'm going to show you how to get that equation in a minute. Okay, and then, so the q plus that comes out of here then goes into the third equation. The h du is this one. So the solution here that I need to evaluate that one, all these terms are from the equation. This is what just came out of the equation here. I stick that one in here, evaluate that one, and then look what we have here. The h du. H is what we want to achieve, and u is what we want to achieve it with. So this is a gradient that we need to improve our h. Okay? This is exactly the gradient we need for the next time to do better. Okay? So this the h du is a gradient that goes into your favorite optimization routine as the gradient. And then it tells us, okay, if you want to have a better h, go down or up the gradient. That gives you a better u, and next time around you have a better guess than you had before. You go through that cycle again until you get another gradient, and you go around and around and around and around until that gradient is going to 0, as it should. Okay? And then it says, okay, you just climbed a hill or you're down in a valley. This is your optimum. Okay? All right. Now, this was in all generality, okay? So we're no longer restricted to linear time invariant systems or Floquet systems of any kind, okay? I have not specified F. I have not said it has to be linear. We didn't need that one, okay? I didn't have to say this is autonomous in time. It can be time varying. It can be anything you want to. So at the moment, we're totally free to use F or H, okay? So both the equation can be anything you want to, and what you're after can be anything you want to. Okay? So we can treat time periodic flows, for example, turbomachinery, blade passing, okay? Pulmonary flow, hemodynamics, time varying inlet flow, ramp-up flows. Okay? You can have nonlinear flows. This F can be nonlinear. I'm going to show you an example later on where we have a nonlinear flow. Okay? Mixing. They can even be stochastic with some uncertainty thrown in. Okay? You have to formulate it a tiny little bit differently to go statistical, but nevertheless, that framework can more or less handle anything you throw at it. The optimization may be difficult, but certainly you can write down in all generality, what you would like to know about your fluid system. All right, so these Lagrange multipliers here, that's the new concept. Okay, so suddenly we're getting a second equation that wasn't there before. So we have to ask ourselves, was this just a math trick to get the optimization going? Or do these equations, this second evolution equation for the adjoint, is there something in there that we can actually use all by itself? Okay, what is the role of these Lagrange multipliers? Now, the Lagrange, the adjoint variables, all the variables that are needed in here are independent flow fields. They have their own evolution equation. And that evolution equation looks a little bit like the Navier-Stokes equations, although not quite. Okay? And what they do is they provide sensitivity and gradient information, because that output from the adjoint variable went straight, not quite straight, but multiplied into our gradient expression at the end. So they must have something to do with a gradient, with sensitivities. Okay, so let me bring that home a little bit more. Okay, let's say I have my cost here that I'm going to abbreviate as I, and I'm going to make a small change to my equations. Okay, so instead of q dot minus f, q, and u, I'm going to add a little bit of a forcing term on the right-hand side. Okay, that could be some bump on the wall, that could be a free stream perturbation, that could be a gust that comes by, anything you want to, but it's going to be external. Okay, so if I change something here, it will shake off my cost functional here and the Lagrangian there as well. Okay, that's one way of doing a small perturbation. The second one, so it's an additive perturbation. The second one I can do is, I can do an internal perturbation. I don't add anything to the equation on the right-hand side. I mess up the terms in the equation. Okay? So my small f is actually multiplied by q. Somewhere in here, I make a small change, and that could be I change the Reynolds number up by 1%. Okay? Or I change the mean flow a little bit. Or I change the Mach number. I change the geometry. I'm going to show you some examples later on. Okay? So this is an internal where I mess with the equations. This is an external where I leave the equations and add something to it. Multiplicative, additive. It doesn't matter. If you cancel all the ones out here that cancel, so the q dot f cancels the I, because that's how we computed it. Okay? You actually get a link between the changes you make to the effect it has on the output. Okay? So this is the change I make additively. This is the piece I add, and this is how it impacts my drag, for example. Okay? And you see that the proportionality between what I perturb it with and what the result is Q plus. So it acts as the proportionality between input and output. So the higher Q plus, the more I will mess up my drag. Okay? So if I look at the Q plus field all by itself, it immediately identifies, oh, if you do a small perturbation here, it will have a huge effect on drag. If you do it here, nobody cares, right? And where it's 0, I can do whatever I want to. It will not have any impact on the drag. Okay? Same thing here. If I change something in the equation itself, that impact here, again, is multiplied by Q plus, but also by Q. Okay, that's the only difference. Here, it's just Q plus. Here, it's a scalar product between Q and Q plus. Okay? All right. So adjoint variables carry information by themselves. You cannot just use them for optimization. It's worth looking at them all by themselves in isolation and determine where in your flow do you have a sensitive area and where you don't. Okay? So they carry information all by itself. That's very nice, because with this additional information, with solving that additional equation for the adjoint, we get an enormous amount of information that we didn't have before, that doesn't come out of the first equation. Okay? And because of that one, we can ask very, very different and very complicated questions that are often not asked in stability theory if you do it the classical way. The classical way, you just care about thumbs up or thumbs down. It's a binary decision. Is it stable or not? Is the eigenvalue in the half-plane that is unstable or the half-plane that is stable? Here we can ask a little bit more intelligent questions. For example, what are the most stability-sensitive areas in the flow? The adjoint will point to that. Does the stability receptivity change as we change the equilibrium point, as we change the geometry, as we change a parameter? Is it getting better for higher Reynolds number, or is it getting worse for higher Reynolds number? What effect does the Mach number have? All these things can be asked because we have gradient information. Okay? For a standard stability analysis, you would have to do another calculation with a higher Mach number if you want to know whether it's getting better or worse for a higher Mach number. Here, we don't. And I'll show you examples where we can get actually parameter studies at almost no cost whatsoever, within reason. Okay? Also, another question that often comes up is if you have an instability and you actually see the mode that grows the most, okay, where the mode grows the most is not probably where it came from. It came from somewhere else, and by the time it grew to high amplitude, it already moved away from the origin of where it started. Okay? This technique with the sensitivity actually can tell us where the origin of an instability is. Okay? Or another way of saying that one, if I want to kill that instability, where should I kill it when it's still small? Okay? Where did it come from? Where can I sort of suffocate it while it's still developing? Okay? So for control purposes, this is very, very important information. And also, of course, where should we place control elements to efficiently manipulate the flow, and many, many, many more. Okay? So this is the added value that we get. We can do a much, much more complex stability analysis or flow analysis. And eigenvalues and asymptotic tools that we had based on Lyapunov just cannot do that. Now, okay, before I show you some examples, let me also say a few words about the computational details. Because I just threw out that math and say, here's the adjoint equation. Well, yeah, how do I get that, right? And if I do nonlinearities, is there any other things I have to watch out for? So here's a little bit of an overview of what needs to be done to do this type of analysis in the modern way, like I have in the title. Okay. So this is the system we have to solve, obviously. It's that iterative round and round and round thing where you have a simulation here, and then you have to solve the adjoint equation, then you have to solve the gradient, stick it into an optimization, do better next time, and then go around and around until you have what you want. Okay? So usually what we have is something for this. This is your code, okay? And it could be OpenFOAM, or it could be your self-knitted code, or something like that. It could be a house code, legacy code, whatever you have, okay? So this is your code. This is what you probably don't have, or probably have not even thought about, okay? And this same for this one. The optimization, I assume you just take something off the shelf, BFGS or conjugate gradient or something like that. So the question is, how do we get these components to solve this equation in the best possible way? Okay. And one possibility, there's many possibilities, but one possibility is you sit down and you derive it. Okay? You take your equations and you just go through exactly that integration by parts to figure out what is this equation, this FDQ, how does that look like in my case? Now, if you have the incompressible Navier-Stokes equations for a simple geometry, that one has been done for you. Okay, there's plenty of papers out, and you can even do it yourself for an afternoon, and you have it done. Okay, but if your F happens to be the compressible Navier-Stokes equation with reactive flows and non-equilibrium and multiphase and level sets, good luck with that one. Okay, you're going to be busy for the next 2 years, and you better buy sheets and sheets of paper. Okay? So there has to be a little bit of a better way of getting these things from your code. Okay? Now, one thing, and then here is how we do it. Okay? So one possibility that often comes up that people are probably familiar with is automatic differentiation. Okay? How many of you have heard of automatic differentiation? Very good. Okay, so automatic differentiation is a way of getting sensitivity information, getting the adjoint, by going through your code and producing from your code another code that solves the adjoint equation. Okay, and it does that automatic, as the name suggests. Okay, so typical one, ADI4 is a package. Tapenade is a package that is quite good for these things. But the problem with automatic differentiation is you send your code that is already big, like a compressible Navier-Stokes code with shock capturing and everything, okay? And then the code that comes back after that software package works through all your subroutines is enormously inflated, okay? And also is quite slow because of that, okay? And if you look at it, to go through the code and actually learn what is it actually doing, it's a little bit like a black box, okay? So we wanted to have something that is much leaner and something that we can actually do fairly easily with our code, okay? So the FDQ, this thing here, as we know, that's the Jacobian, okay? That's the linearized Navier-Stokes equations. It's not exactly what we need, the FDQ. We need the H of that, okay, the FDQ. But let's just go in two steps. First, I do the FDQ, and then I say, if we have that one, how do we get the transpose of it, okay? So the Jacobian is the FDQ. This matrix is generally not accessible, so we don't form that matrix. All we need is a matrix multiplication with that matrix. So I want to have, I'm totally happy with a routine where I give it a vector, Q, and it gives me back the vector that is multiplied by the Jacobian without ever forming the Jacobian, okay? So only matrix vector multiplication is necessary, okay? And the only assumption that I make is, and I should not even mention that, the code should be nice and modular, okay? Not just one big main code, nice subroutines that separate out the different tasks in your code. Okay. So let me demonstrate how that works, how that technique works on a very simple code example. Okay. So let's say somewhere in our code we have the following snippet. It's a little code fragment. Okay. This is one time step, so we go from Q, our field right now at time step T, and this is the DQDT that we have to go into our Runge-Kutta or whatever else time stepper you have. Okay. So this is the flow field. Let's say we take an X derivative, then we go through a nonlinear subroutine, F1. Whatever comes out of the air, we take the Y derivative, and then this piece and the ddx of the first piece go into a subroutine that takes two arguments and is also nonlinear, and that's our Q2, and that's the right-hand side for dqdt. Let's just say this is a little piece of our code. Could be much more complicated. Okay. All right. So, like I said, I'm going to do two steps. The first is the Jacobian, and then I transpose it. Okay. So if you do the Jacobian, we realize that ddx is a x derivative. That's a linear operation. Okay. So if I don't need to linearize that one. It's already linear. Okay, so no linearization here. This is a nonlinear one. That needs to be linearized, and that needs to be linearized. But the ddx and the ddy are linear operations. Okay, I don't need to do anything about that. Okay, that's very good, because we realize that the ddx's and the ddy's are the operations that link grid points together. Right? They link grid points together. I plus 1, I minus 1, things like that. Okay, eno, veno, whatever. But the nonlinearities most likely are local on the grid. Okay? They don't link the grid points together. You very seldom have a nonlinearity that actually is one component here and then another component from another grid point. Very, very seldom. It's a for example, a reactive term is on the same grid point. Okay? So that's very good. So in order to linearize that one, we do a very simple finite difference approximation where we say F1 and we call that subroutine twice. Once with the part we want to linearize about, and the one with a small epsilon perturbation divided by epsilon, and then this, calling it twice the same routine, is the same as multiplying the E with the Jacobian of that subroutine. Okay? That's the trick. So by replacing this one, this routine, by a double call with a small epsilon, linearized around a Q0, and if Q0 is the same thing all the time, I can do it once and store it away, but I also can do it on the fly. Okay? I can basically replace all the nonlinear parts by their finite difference equivalent, and then my whole block diagram looks like this. Okay? So this was a nonlinear routine. By calling it twice, I linearize it. This is already linear. I linearize this one, and I linearize this one. So now if I go through that part here, and I patch it together like this, so the A1 is here, then the DDY is here, the A21 is here, A22 is here, you plus it, DDX of Q, then this linearized network is exactly the Jacobian. Okay? So I do automatic differentiation surgically, piece by piece that needs it, and not the pieces that don't need it. Okay? So if I go through that one, I just did, instead of solving dq/dt is f times q, by replacing the routine calls by its matrix equivalent, I just linearized my code. Okay? But the linearization is not what we want. We want the transpose of that one, right? So now, forget about this block diagram. If I transpose this expression here, okay, all together, so I slap an H on top of that one, this is what happens. I get an H on every single piece, plus I reverse the order. Okay? That's what transposition of products does. Okay? All right, so this is really what we're after. But now, if you look at this one, you have to read it from right to left. This one basically says, first I have to do A22, then A21, then Y, then A1, and then the X at the end. Okay? So what that means is I have to revert the order of my block diagram. I have all these matrices, so transposing them is a piece of cake. Okay? So I just have to run through my code in reverse order and call the transpose of the matrix that I linearized. Okay? That's it. So that means that if you have a right-hand side call that consists of calling routine 1 and then 2 and then 3, for the adjoint you have to go through and call your routine 3 first, then you're in transpose mode, then your 2, and then your 1. So you run through your code in reverse order with transposing every routine that you have. And that one automatically creates an adjoint time step. Okay? That's very convenient because every time I change my code, the adjoint comes with it. Okay? I add another routine. I just add another routine into my block diagram. I don't have to derive anything. I add a reactive module for burning gases and so on, and it gets automatically adjointed in the code. We don't derive anymore. We actually take the adjoint of a code in block diagram form. Okay? And we run forward to get the forward solution, and we run through the adjoint code in reverse order to get the adjoint time stepping. So the efficiency, the linearized code and the adjoint code are approximately the same size. There is none of this explosion that you get with automatic differentiation. Okay. The matrix extraction step adds only a moderate fraction. Okay, so you have to linearize on the fly. That one is usually done locally. You can store the matrix, or you can. It's so cheap. It's not even don't even bother storing it. You can actually, generate it whenever you need it. Okay, it's so fast. And it works really, really well. And your adjoint is up to machine precision. You don't bother with boundary conditions, which usually are the killer in deriving this one. Okay, everything is lumped together. A few extensions. I said differentiation is a linear process, so we never bother linearizing our ddx and ddy matrices. Okay, that's not always true. You can actually have upwinding or Wano, where you have a switch. Which way you go in the stencil, in that case, you have to linearize the switch, but that's no big deal. You can also throw in turbulence models, okay, and linearize and adjoint the turbulence model. That one works just as well. Spallard-Almaraz, just choose it up, okay, or compressible flows. Okay, the second thing I wanted to mention about the implementation. So now we know how to get the adjoint. There's one more thing that really can give you a headache, and that is what happens, here is your equation, okay? And that's the forward equation for which you have a code, okay? And let's say f is nonlinear. That's the backward equation, and if f is nonlinear, df dq has a q left. Let's just say it's quadratic, okay? Let's say f is quadratic in q, taking one derivative leaves one q behind, okay? And if it leaves one q behind, then this one is q dependent. So in order to solve that one, it has a coefficient that depends on q. So what that means is that on the way forward, let me back up. I also have to, I mentioned one key ingredient. I didn't mention one key ingredient. This is a forward integration. So we start with time 0, and we start forward up to time large t. Okay? The adjoint equation actually is solved backwards in time, from capital T back to 0. Okay? All right. So with this one thrown in order to do the reverse integration from t to 0, I will need all the q's that I actually calculated on the forward problem because I need it for these coefficients. Okay? So suddenly, these two things are not independent of each other. I can integrate the first problem all by itself. I don't need to store anything. But on the way back, if f is nonlinear, I need the forward flow fields to inject into the coefficients for the backward integration of the adjoint. Okay? So that one is a little bit of a bad thing. So there's no free lunch. So how do we do that? Let's do two cases. The first case is I have infinite storage. Okay? So I can actually afford storing all that. So this is usually the diagram that you get. So let me just orient you. This is the time we're going to integrate. We integrate from 0 up here. So time is not going this way, it's actually going down. Okay? Time is equal to 0 here to capital T here. Okay? And this is this is the initial condition, time step 1, time step 2, time step 3, 4, 5, and so on. Okay? And what I note here is the total number of time steps I take, independent of whether I go forward or backward. So I chuck along here, okay, and I store all the flow fields. Every time step is stored away. I have infinite storage, okay, until I get to t. And then I'm at t. Now I have to take the adjoint and go backwards to 0. Okay? So as I turn around and go back up to 0, so that's the reverse integration, back to 0, okay, I need, for the next time step, I need that flow field that I stored one before. Okay? So I inject that one here, and then I can solve my adjoint equation. And I do the next one, and the next one, and then by the time I'm up here, I injected back all my flow fields to do my backward integration. So going down and going up, this is the total number of steps. It's twice for each direction. Okay? That's when you can afford to store everything. But usually only for small problems that works. For large problems, we cannot. So let's do a second one where we actually store only a few of those, okay? So here's the way we do that. Let's say we only have memory to store 6 flow fields, okay? Just 6, but we're integrating much longer than 6 flow fields. Okay? So here is what we do. We store the initial condition, then we integrate away without storing, and then next time we store is already here. Then the next one is here, and then when we see, oops, we're coming to the end of it, then we store everything on that last little piece. Okay? So then on the way back, we do it exactly like we do. We have everything we need until we come to here, and then the next steps, oops, we don't have anything. Okay? So in that case, what you do is you stop your adjoint integration, you use this as an initial condition, you throw this one out, you clear up your memory, and then you start here again to do another forward sweep to fill in the ones that you didn't store. Okay? So you do a little bit of extra work. You take this one, you fill it in, okay, the one that you skipped before, and then you can go further on with your adjoint. Then you come to here, is something missing, you play the same thing again, you're going to take this one, you regenerate this one, then you can keep on going, then you regenerate this one from your checkpoints. Okay? And that's called checkpointing. Okay? So you have to do extra work, so you pay in time what you cannot store. If you could store everything, there would be just as many, you have no extra work, right? Everything is there. But in this case, you actually buy yourself storage by doing the extra work. So now the extra work is not much longer, but it's 50% longer than it was before, and you have to do this extra work. Now, this was not a very smart choice of checkpoints. Why? Because in the beginning, I said I have storage for 6. Okay, so I stored 6, so now my storage is up to the rim. And then on the second one, when I'm here, I have this one stored and this one stored. I only have 5 active checkpoints stored. Okay? And then when I'm in this thing, I only have 1, 2, 3, 4, and here I have 1, 2, 3. So I'm not really using my memory optimally, because when I only store 3, I could store 3 more, and they're empty. Okay? So this was not a good distribution of checkpoints. A better way is distributing it so that in the beginning you skip longer, and then towards the end you skip a little shorter. And there's an optimal distribution where you always have your 6 memory slots full all the time, no matter where you are. Okay? And that one is called binomial checkpointing or minimal repetition dynamic checkpointing. Okay? But you get the idea. All right. Now, special cases. Okay. This is about as general as it gets. I have not said anything. I have not made any restrictions, anything. Okay. This works for everything. But how about special cases? And maybe even familiar cases. Okay. So let's say we have an LTI system, and I think Scott will talk about that one or afterwards. Okay. So we have a linear time invariant system. So my F is not as complicated as you can make it. F is actually quite nice. Okay. And also we're going to look at gains. Okay. So this is case number 1. My governing equation is Q dot is equal to L times Q, and L is constant coefficient in time. It's a linear time invariant system. Okay? And let's say my objective is what I want to maximize is the perturbation in some kind of measure. Okay? Energy, for example, kinetic energy. My perturbation after time t divided by how I started out with. Okay? So that's the overall gain in energy. And I want to maximize that. I want to see how bad it can possibly get. My control variable to play around with is the initial condition. Okay? So I play with my initial condition to make that ratio as big as I can, subject to this evolution equation. Okay? So that's a very special case of that general optimization thing. Now, what I want to use here is this equation, now as nasty as it could possibly be, actually can be written down as a formal solution. I don't have to solve the initial value problem. There is actually a direct map from my initial condition to the endpoint. Okay? And that one is a matrix exponential. Okay? E to the TL solves that equation. So this is the one shot that takes me from the initial condition all the way to the end of the time interval Q of t. Okay? So what we do is we seek an initial condition that optimally amplifies over a specified time interval. That's like a stability analysis, but certainly not in the Lyapunov sense, because we have a finite time interval, and we want to see how bad can it get over that time interval. Okay? If you take that time interval t here and take it to infinity, yes, you would recover the Lyapunov stability. Okay? But as I said, this in most flows, this doesn't make sense. The time scale is set by the flow, and we're going to have a characteristic time step, time horizon t, and we want to know what is the perturbation over that time step, time horizon t, that optimally grows and uses all it can use in the equations to grow. Okay. So now my iterative scheme is actually not going iterative anymore because I have a direct map. Okay? So my forward integration, my governing equation, is now just an algebraic map between my initial condition and what comes out at the end of the integration. But I don't integrate, I just map. Okay? The adjoint can also be solved because now the adjoint also is linear and can be mapped the same way. And that's the solution to my second block. The adjoint equation is another map that takes my outcome from here and maps it back to 0. Okay? Reverse integration in one shot. Okay? There's no need to do time stepping. And then my third box was the gradient expression, right? I stick all of that into the gradient expression, and what comes out? An eigenvalue problem. An eigenvalue problem from the linear, but where the initial condition is actually appearing as an eigenvector, and the gain is appearing as the eigenvalue squared. And this exponential is L and L plus together, so this is the full round trip. Okay? Forward is for L, backwards is for L plus. You stick one on top of each other, you go one round trip. So you start at 0, the L takes you to t, the L plus back to 0. These two together is one round trip from 0 back to 0. Okay? So that's the combined mapping of one round trip. And what you do here is you write down an eigenvalue expression, and what that adjoint looping, this going around and around and around is doing, is basically a power iteration on that eigenvalue problem. That's all there is. Okay? Now, if you break this one apart, so suddenly linear algebra is doing the optimization for us. Okay? So you should be aware of that one. When you calculate eigenvalues or singular values, you actually solve a very specific optimization problem. Okay? Keep that in mind. So this one, if you break that apart, this is e to the TL times e to the TL plus. Okay? So it's a little bit like form like A times A transpose. Okay? And an eigenvalue of an expression like this is the same thing as a singular value decomposition of just one of those components. Okay? And here it is, the SVD of the matrix function. That is classical non-modal analysis. Okay? You take the matrix exponential, you hit it with an SVD, the singular values give you the maximum gain, and the principal left and right singular vectors give you the best input and the best output. Okay? So this is a special case of that optimization around and around. Okay? Second case, let's say we want to have a outside forcing. Okay? So we want to know how does our linear system respond to some kind of a frequency input. That could be an acoustic wave in a free stream, that could be roughness distribution on the wall, anything you want. Okay? So now this is our governing equation, but again, an LTI system with linear time invariant system matrix. And now our objective is, okay, I want to play around. My control variable is how do I force? And my objective that I measure with is the energy of the response divided by the energy of the pumping. Okay? So this is the internal amplification of the system, given a certain frequency. The frequency you dial in, that's a parameter. Just like before it was the time horizon. Okay? So this is what you have. So we want to see what frequency resonate with our system in a sense, but I don't want to overuse the word resonance. Okay? It has a bad connotation. So we seek an external driving that produces an optimal response at a specified forcing frequency. And just like before, this thing doesn't need to be integrated or time-stepped. It's linear and time invariant, so that means I can actually write down an equation for that one that maps it directly from forcing to output. And that one is like this. The matrix resolvent does that. Okay? So I omega minus L inverse maps the forcing directly to the output. Okay? So no integration there either. And then you can go through the same thing, okay? Since this is my box for the governing equation, no integration, a direct map with the resolvent. This is my adjoint equation, no integration, a direct map between the response and the adjoint forcing. Okay? Then you stick everything into the gradient box. Okay? And again, you get an eigenvalue problem. The forcing, the control variable, the forcing comes out as an eigenvector, and the gain comes out as an eigenvalue squared. Okay? And this is the forward mapping, and this is the backward mapping, just like before. Linear algebra is doing all that optimization for us. Okay? And the same thing, the SVD of the resolvent gives you everything you want. The singular values will be the H's, and the singular vectors will be the QFs and the QRs. Okay? One shot. So you probably have seen this thing. You may have even done these things, but there are actually special cases of an optimization that is much, much more powerful than being restricted to LTI systems. Okay, so little summary. What you probably learned in a hydrodynamic stability course, if you learned Orr-Sommerfeld equations and things like that, Rayleigh criterion, inflection points, and so on. This is modal analysis. So that means we're looking at the eigenvalues of matrix functions. But you should remember that this is a T to infinity analysis. You have to judge whether that makes sense for your flow or not. Okay? Mostly it doesn't. The few cases where it does make sense or you get away with it are very, very rare. Okay? So that's modal analysis. The next more general thing is non-modal analysis. You have a finite time horizon that makes already more sense, but you can only apply that one to linear time invariant systems, but you replace the eigenvalues by the singular values of the same matrix functions. E to the matrix exponential or the resolvent, or there's many other ones that you can use. Okay? So that's already a generalization. But the best generalization is to let go of almost everything and go optimization-based with that direct adjoint looping. Okay? And then you have finite time, you have nonlinear, you can handle nonlinear equations, time-dependent systems with the tool of choice, which is that direct adjoint looping. And I'm not saying this doesn't take more effort. Sure, the derivation of the adjoint, all these implementation things, the checkpointing, all that costs a little extra, but you get so much more out of it. This is more or less useless information if you have a complex flow. Let me show you a few applications. Okay. So the first one, I'm going to show you 3 applications and a few more, another one later on. That one is total noise. This was joint work with Miguel Fosas de Pando from Cadiz and Denis Sip from Honorat. So this is the thing. You have an airfoil, NACA 0012, 12 degrees of 2 degrees angle of attack. Mach number is 0.4 and the Reynolds number is 200,000. That puts us into the glider range. Okay, it's not an airfoil. You don't see this phenomenon on a A380. But if you have a glider airplane, that's about the range you have. And if you're a glider pilot, you actually know about tonal noise. Or wind turbines. Okay, the annoying noise that wind turbines make, that's from an instability like this. So this is how it goes. We have an instability of the boundary layer on top, and we have an instability of the boundary layer on the bottom. Okay. These two instabilities roll down and meet each other at the trailing edge, where they slam into each other, high shear. The high shear generates an acoustic wave that radiates in all directions, also upstream, and at some point re-triggers that instability. Okay, so we have a feedback loop between hydrodynamics and acoustics on the top and on the bottom. Okay, two feedback loops talking to each other through the trailing edge. Okay, analyzing that one by doing local analysis, and it has been done and has been published, by slicing the boundary layer here and doing a modal analysis with eigenvalues of the boundary layer here doesn't really capture anything that is essential for this type of mechanism. Okay? So the way we do that one is we're using our sensitivity analysis between the forward solution and the adjoint solution, and we ask the question, given a frequency, so this is the resolvent analysis, given a frequency, what is the most dangerous input? Okay? So if you do that one, this is the most dangerous, this is the optimal response, the things that come out that are stimulated at a specific frequency the most. Okay? And you see that this is a modal solution, or this is a coherent solution that has all the features that we're actually expecting to contribute. So it has the boundary layer instability on top. Here, it's rolling down. There's also a boundary layer instability here, but it's so small, it only amplifies almost on the last little piece here. You see it here. Okay? So it doesn't do anything, and suddenly, whoop, in the last one, it really goes up. Then you have the acoustic wave radiating, nice dipole here, radiating forward and triggering it again. Okay? So now if I ask you about the origin of this process, okay? Because this is the process with the highest acoustic component. That's the loudest mode we found. Okay? And if I ask you, where does this thing come from? If I want to kill this one and make the airfoil more quiet, what should I do? Where should I place something? The regular stability analysis has nothing to say about that. You have to actually go to the sensitivity information for this structure and see where its adjoint lives. Okay? And this is how the adjoint looks like. This is it goes backwards in time, as I said. Okay? So this is the sensitivity information for this mode. Okay? So disturbing this one, people have tried to put little bumps up here to disturb that boundary layer instability up there. Did not make a difference at all in terms of making it more quiet. Okay? Sometimes it even made it louder. Okay? But then there was a long time ago, there was a Japanese technical report that never made it into the main literature. They put a wire and put the wire, just traversed with the wire from here all the way to there and down on the bottom. And when they came to this spot here, suddenly the airplane went totally quiet. Okay? So if you want to kill this one, this is the question for the origin of an instability or the weakest link in the feedback loop. The adjoint and the sensitivity information actually gives you that information. This is the place where you put the wire or a bump or something or an actuator to kill this one. And this is the weakest link of that feedback loop. And it's not on top. It looks like something is happening on the top. That's just a sideshow. Okay? The real sensitivity is in the bottom. Same thing goes for a second example, a boundary layer receptivity. Let's say we have a boundary layer, very, very classic. Many papers written about that one. And you have a bump here and a bump there. And you have a compressible boundary layer. Okay? Mach 0.3, Reynolds number of 1,000,000. And you want to know something about the resonance, acoustic resonance between these two bumps, okay, and how to manipulate that one. This is the part that you have from the forward problem. It's unfortunately not animated, okay? So this is the same thing. This is the forward problem. This is the first box. This is the second box with the sensitivity that goes with it. And if you superimpose the two, you actually get, as you expect, a frequency response that has these peaks, okay? So everything here, when it peaks, there's a constructive interference between these two. The two waves constructively interfere and amplify each other, okay? Then for other frequencies, the wave number from here to there doesn't fit in a integer multiple between the distance, okay? And that's why you get a trough here. And then it fits constructive, destructive, and so on and so on, okay? So the nice part about that is also this was calculated with the direct and the adjoint. The adjoint has the sensitivity information, okay? It has the sensitivity information to any changes you make with the equation, okay? So we have the Q plus, and we have the Q, and now we can play with the equation any way we want. That means we can now say, without any more simulations, without any more calculations, we have everything we want. We say, what happens if the Reynolds number goes up by 5%? Well, we just take all the terms in the equation that are multiplied by the Reynolds number, and we take our solution for the direct problem in the adjoint, we evaluate that scalar product, and we know what will happen. Okay? Then we say, okay, how about changes in the Mach number? Well, we take all the terms that have Mach numbers in it, okay, and multiply it, and so on and so on. So what we did is we wanted to know if we change the distance between the two bumps, what will happen to this curve, okay, the amplification. And usually what you have to do is you take the bump a little bit further, you do the whole thing, the whole calculation again, and then you get a second curve, okay, and then you see how that second curve changed. But since we have the forward and the adjoint problem, we have everything we need. So our delta F are all the terms that make this distance larger. And this is the curve we get. This is the change in G, in that amplification, divided by the changes in the distance between them. Okay? This is the curve we get. And we get that just by evaluating that expression. No new simulations, no new stability analysis. Okay? So once you have that, if you look at this one, wherever that thing has a peak, it's going to go through 0 here. But it's on the left side of the peak, it's always positive. On the right side of the peak, it's always negative. Okay? So this is the first term of a Taylor series expansion. If I multiply that one by delta xd, I get the delta g that I can add to my curve. So if I do that one, I know that all the frequency peaks move to the left, okay? Without doing that calculation again. And I can play around with that with any changes I can make to the equations. Okay? So there's a lot of information in that adjoint. It's worth calculating it because then afterwards you can ask any question you want about parametric instabilities. All right, third example, spark ignition. That's joint work with Ubay Quadri from Cambridge. So the question here we had is, let's say you have a flame and the flame blows out. That's a very dangerous condition for a pilot. You're up there, engine goes out, you need to restart the engine. Okay? You better, if it's a fighter pilot, you want to have it restarted on the first trial, right? So you want to do it as best as you can. Okay? Maybe a commercial airliner can try a few times, but a fighter pilot needs to have an engine to get away. All right, and we also use the optimization-based framework. Okay, so here's just a simulation. That's what happens. We can have a little spark here. Okay, and the first thing is the kernel generation. So it's a little hotspot, if you want. Okay, then the whole flame expands. Okay, it reattaches back to the nozzle. Okay, So it attaches here, and then it blows to the right, okay, until it reaches the domain, okay, flame expansion, and then it sort of bounces back, and then eventually the flame stabilizes and settles into a nice flame back reattached to the nozzle, okay? So the question is, where should we put that sparker so that we can get to a fully established flame as quickly as possible, okay? So our cost objective is the integral over a specific time if we integrate that curve here, we want to have as big an area as possible underneath it. Okay? And then we go around and around with that direct adjoint thing. Here's a spark, okay? And then here is the forward simulation. The whole thing blows out, okay? Then we're going to stop that. That's the time horizon we picked, okay? Then we go over here, and then we propagate that one back with the adjoint reactive compressible Navier-Stokes equations, okay? So as I said, this is a reverse in time. So first it blows out, and then the adjoint sucks it back in, okay? And by the time we get to 0, out of this mess here, we extract the gradient of how to move this point so that next time we're going to go through that process a little faster, okay, and a little steeper in that curve, okay? And you build that up and up and up, and then here you have all the iterations, and you see that the iterations nicely follow the stoichiometric surface as they should. That was just a little bit of a test problem. Now we're doing a lot more complicated configurations in a lifted jet diffusion flame. That's work in progress. All right, so this one brings me then to a few extensions. Okay, so these were like a little bit like bread and butter applications of that framework, the optimization-based framework. So what else can you do? Can we actually push it even further than we already have? Okay, and the nice thing you can do about that one is here we have the objective, here we have our equation constraints, and I reverted back to linear time invariant just for convenience. You can just as well write a nonlinear equation here and do the same thing. Okay, so don't be too stuck with that. Okay, so we have two things that we can actually do. The equations are always the same, okay? So there's not much we can do here. It's already good that we can enforce the nonlinear equations. So let's see what can we do here and what else can we do. So what we can impose a different norm here. This is the 2 norm. This is the energy norm, okay? The energy after time t divided by the energy it had before. And by doing the energy, it's sort of the go-to norm for incompressible flow. If you don't have any better idea how to measure a perturbation, you say energy. Okay, energy is nice and L2, but it has some disadvantages, and that one is because we harvest energy, we're not restricting the size of the initial condition or the size of the output. Okay, so by saying maximize the energy, the structures usually spread anywhere in the flow field wherever they can get some energy. Okay? They can get their hands on some energy. Okay, so usually energy is linked with shear. Just by displacing shear, you can actually create energy. Okay, so if you have an optimization and there is a big shear layer that goes really long, like a separation bubble, you're going to get a structure that spans the entire separation bubble, okay? Because since you maximize energy, it really takes every little bits and pieces that are available from the flow to create as much energy as it can. Okay? So these structures got pretty big. But sometimes in practical applications, we're not so interested in these large structures. We want to do a worst case analysis. We want to see where in the flow is a dangerous spot, okay, that generates a localized disturbance that is dangerous in terms of growing. Okay? And the large ones are often growing better, but they're just a little bit too contrived. Okay? So we want to change the norm here. We want to measure this part not in a 2 norm, but in something else that compactifies our input and our output. Okay? So changing the norm is a big thing because I have a sketch here. So let's say our constraint is somewhere on that line. So that means all the solutions that satisfy our equation are on that line. And that line is always the same because the equation is always the same. But based on how we measure the objective, which is the closeness to the origin, that depends on how we measure closeness. Okay? And if you do a P1 norm, then this is the solution that is optimal. If you do a 2 norm, this is the solution that is optimal. And you see that if you do an infinity norm, this solution is optimal. So you have a solution, but it slides up and down your admissible space. Okay? So if you try that one, this is what you do if you have an optimization with a 2 norm, okay, energy. And that one is very simple, channel flow, very boring. Okay, and that one is the part, I think Javier talked about that. This is the OR mechanism. This is the best input, and this is what happens to it. Okay, and you can see that the input is everywhere, and the output is also everywhere. It fills the entire domain, okay, because it's energy harvesting. And the best place to harvest the energy is everywhere here. But now if you say, no, I don't want to have the energy to be harvested, I want to have an infinity norm that localizes the structure in one spot. Okay? If I just get to pick a perturbation that is in one spot, where would that be? Okay? And this is how you do it. P infinity is, this is the input and this is the output. Okay? So you can localize and really zoom in into parts of the flow field that are particularly prone to localized instabilities. Okay? Now, this is P infinity. For that one, there is not even an SVD that exists for P to infinity. SVD needs an L2 norm. Okay? Energy. Eigenvalues need an L2 norm. You have to do optimization if you're interested in anything else than a 2 norm. Okay? So infinity norm, if that's what you want, there's no way, there's no linear algebra that is linked to an infinity norm. This is another recent work that we've done with Max Egel, my student, as now a postdoc in Princeton. This is mixing of a binary fluid. So we were interested in a 2D Petri dish of that sort, and then we have 2 cylinders on circular paths, and they go around, and then they mix up the fluid. So we have the blue fluid on the bottom and the white fluid on the top. And if you do everything right, they should all mix together nicely. Okay? And we wanted to optimize that mixing by optimizing the path and the velocity on these circular paths. Okay? So this is exactly the same thing. This is the hydrodynamics. We also have to have an equation for the tracer. This is a nonlinear PDE. We have to do checkpointing. Okay? There's no way around that. This is the adjoint, the sensitivities come out, the optimization, all these things, you should be familiar with now. Okay? So the mixing strategy is what we want to play with. But here is the thing. Mixedness is measured in the best possible way by this norm. So I take the passive scalar, I take the minus 2/3 derivative of it, whatever that means, okay? Absolute value, and I integrate over the entire domain, okay? This is a negative Sobolev norm, fractional norm, it's called, okay? And that one, the mathematicians tell us, is the best way of measuring the mixedness of a binary mixture, okay? This is what we want to optimize because that goes right to the core of mixedness, okay? No proxy. It does it right away. Okay. So again, this thing is messing up everything. First of all, 2/3 derivatives come into the equations. You have to deal with that thing. And on top of that, there's certainly not a linear algebra SVD that is made for a 2/3 derivative. Okay? It's only for 2. Okay? And on top of that, this is a nonlinear PDE, so we're nonlinear. We cannot even talk about anything about SVDs or eigenvalues. You have to do the optimization. So this is what happens. Okay, this is the path optimization. This is the mixing, and the 2 cylinders don't go through the interface. They actually go back and forth to generate shedding vortices and stopping vortices and let the vortices do the mixing. That's the best strategy. We would have never guessed that one. Okay, that's a total surprise. We would have thought the cylinders just plunge through it and stir the whole thing up. No, they don't. They just jiggle a little bit in the beginning, send all the, it's like a vortex cannon, right? They send all the vortices towards the interface and let the vortices that they shed do the mixing. That's the best strategy, okay? And when we saw that thing, look at this. It's a finite time horizon, so they get only to do it a certain amount of time and with a certain amount of energy, okay? And then they do the mixing, okay? Who would have guessed that? But the nonlinear optimization found that solution, and if you think about it a little bit, it actually makes sense. Okay? You can also do shape optimization, so we turned these things, and in the beginning they all looked like these guys, okay, like hypercycloids. And then we had a certain shape of it. We said, okay, form it any way you want it to do better stirring over one revolution, or I think it's one revolution or two revolutions, I forgot. So let's see how that one does. Okay, so this is an optimized shape for the time horizon with a given rotation speed. Okay, within the constraints. Okay. So you can do anything you want to with that optimization thing. And I realize that this is not stability in the traditional sense, but it certainly uses sensitivity and receptivity and susceptibility information from the adjoint to get the job done. Okay? And you learn about a fluid system by optimizing it and see how it responds, what it likes to do best as you constrain it. This is how you learn about a fluid system. Oops, okay, still turning. Okay, and then on top of that, so this one is basically making modification to this one to go wild, okay? What about additional constraints? You can also say, okay, let this one be energy if you want to, but I have additional constraints that I also want to satisfy. So they would go on the right-hand side, and there's really no limit of what you can add. Okay? So for example, you can say, I want to have a sparse localized stability structure. Then you add a zero norm to here. The optimization gets harder. The adjoint gets harder to evaluate, but it can be done, right? The flexibility is there. You can also have a low-rank stability structure if you penalize it with the nuclear norm. Or you can have some that is the smoothest possible one. Okay? So you penalize the total variation of your initial condition. Okay? And you can throw in anything you want to on the right-hand side. Okay? So for example, you can say, I want to have a structure that is least sensitive to changes in the Reynolds number. So that asks for robustness. Okay? Things of that sort. So the possibilities are almost limitless. So, in summary, theory over the historically has moved from generic flow configurations, right? The days of the Poisson profile are more or less over. Okay, now we're doing DNS and LES and detached eddy simulations. We can do DNS with multi-scale, multi-phase, reactive flows, hypersonics, non-equilibrium, whatever you want to throw in. We can actually simulate these things. Okay, so theory has moved on, CFD has certainly moved on. Same thing with experiments. We started out with hot wires, smoke visualization, Schlieren, very low key, and they still have a place. Okay, but now we also have much more insight into flows from an experimental point of view with TOMO PIV and time resolved PIV and PTV and so on and so on. Okay, and for that reason, I think flow analysis also needs to move on. It needs to move on from looking at eigenvalues and exponential growth and resonance. A good step was already sort of to throw in back that finite time horizon of a stability and redefine stability and move and abandon the Lyapunov concept, which doesn't work so well for fluid mechanics because we have limited timescales. And now go one more step and throw in that optimization-based analysis, realizing that these two things are just special cases. So let's go back to the general case that meshes up with all the things we do in experiments and theory, and then do the stability analysis based on the optimization. So thanks for your attention.
Thank you very much for this excellent lecture. Questions? Who wants to start?
It's it's not obvious to me. How do you define the initial condition for the backward problem? Is there any restriction with respect to the objective?
Yeah, the initial condition for the backward problem is the output of the forward problem. Yeah,
But
that's automatically given. Yeah, that comes out of the derivation.
okay.
So
there's no restriction to the objective.
No, there's no restriction and there's no choice either. There's no choice either. It comes right out.
Okay. Thank you.
Mm-hmm. Yeah.
There.
Yes, there is. There is. So in the question was, can you do that with experimental data when you don't have a governing equation? So the cost objective is still the same. It's what you want. Okay, the constraints are the same, but now the equations will be replaced by conformity to data. Okay, so you will have a data matrix minus the breaking apart into the coherent components. Okay, and you have to basically say that you don't have to stick with an equation. You have to reproduce the data at the end. That's your governing equation, is your data. Yeah. But then you can write down exactly the same thing for data-driven analysis. Yes, there is. Yeah. This was very much model-based, but there's also a data-based version. Yeah. Very good question.
I just wanted to say, first of all, thank you so much. That was amazing talk, and I got a lot out of it. I work in combustion instabilities, and we are exactly in the same, following the same path in the sense that we're looking at modal analysis and linear stability analysis and things. And from the talk, I'm kind of like, wow, we can actually just solve this problem just using brute force, basically, and it opens a whole possibility. So thank you.
Yes,
my question is about how sensitive the adjoint solver is to noise in the flow solution. Could you perhaps do some kind of data compression to basically get around this problem of having to store all the fields for a complex problem?
You can. In that case, you would get a gradient that is suboptimal. So that one is an optimization based on subgradients, it's called. So you can compress the adjoint part, and then get an approximate gradient that points you in the right direction, but not into the perfect direction. So all you do is you sacrifice the accuracy of the gradient, and you have to do maybe a few more loops to really get down to the same optimum. Yeah, but
it's kind of a suck it and see kind of thing.
But
you have to try.
Model reduction. That's one of the things that we're working on now too. Is how can you speed up the adjoint calculation? Do you really need the exact gradient? This is somehow related to, let's say you have a Newton solver and you have a quasi-Newton solver, right? It's the same idea. Eventually you get to the same solution, but the Newton solver gets you the exact steepest descent gradient, whereas the quasi-Newton solver gives you an approximation to the gradient. It's good enough, mostly, especially if you get close. Can we do the same thing with the adjoint? Because the adjoint is a gradient. Can we get away with a few shortcuts on the adjoint and still go to the same minimum? Okay, that's a very good question. Model reduction can be thrown in there. We're playing around with parallelization in time and so on. That speeds up quite a bit the calculation on the adjoint.
Great. I think I have like 50 years of work to do. Thank you.
Me too. Yeah.
Okay, thanks for the amazing talk. The question is, you are going backward in time, and I'm here.
Yep.
And so maybe I missed it, but if I understood well, we are going backward in time because we have taken the original algorithm, the diagram, and then we split it, and then we found that to have it transposed of the Jacobian, we have to flip it.
Yes,
and so
correct.
that's the reason why we're going back.
Correct.
Okay.
Correct. Yes.
But what if we have the Jacobian?
What if you?
We by chance, by magic, or maybe the system is easy enough, or maybe I have a good mathematician, can I have the forward Jacobian itself without, I mean, is it strictly needed to go backward in time, or is it just a shortcut from a numerical point of view? Maybe
It's needed to go backward in time. If you have an evolution equation that is forward in time, the adjoint has to be solved backward in time. That one goes together.
I missed some point, but maybe I can ask
Yeah,
you more later.
maybe
Thank
at the
you.
coffee break. Yeah, I can fill in a little bit more details. Yeah.
More questions? Fabio, you had one also? Oh, try
If you just yell, I can repeat the question.
Yell.
It doesn't work.
Okay, I just want to ask a couple of questions. It seems a bit silly. So the first one is about the discrete and continuous adjoint, whether there's a difference between the two.
Yeah.
And how do you guarantee the self-adjointness of some kind of operators in the discrete case? And whether are we obliged to basically resolve the correct equation of the adjoint? We're just optimizing it. So as long as the gradient is going to a minimum, we're not obliged to be mathematically compliant with the operator.
That's correct. Yeah.
And the second,
Yeah.
a bit more concerned with the topic of the lectures, what is your opinion on the reinforcement learning optimization with respect to adjoint, more classical methods?
Right. Okay. So the first one, difference between continuous and discrete adjoint. That's sort of a big debate, and it splits sort of the community into two religions in a sense. The continuous one has certain advantages of having specific terms in the equation that can be identified with certain physical processes. The discrete one is just flipping the whole matrix, right? So there's not much that after you flip the matrix that you can still identify as bits and pieces of an equation. The discrete one is much more convenient from a computational point of view. If you just want to get the gradient done to keep your optimization going forward, then the discrete one is a little bit more convenient. Also, the way we compute it is much more convenient. Okay. There's also subtle differences between the continuous and the discrete one that I can go into. The second question about reinforcement. Reinforcement is using a proxy for the adjoint. Okay, so it's if you do, for example, stochastic gradients or something, then this is getting the same information by many forward problems. Okay? So it's putting together information that the adjoint gives you with different means. Okay. The disadvantage of this one is also that I should mention and should be honest about is whatever optimum we find here is a local optimum. It's not a global optimum, right? But any gradient-based information cannot give you a global optimum, cannot guarantee you one, because most of the time we're non-convex. So we get stuck in a local minimum rather than a global one. And reinforcement learning, depending on how you do it, has a better chance of arriving at a global optimum rather than a local optimum. Yeah, I think that's probably the biggest differences there are. Yeah. One thing we also look into here is doing that optimization derivative-free. Okay, so the technology for derivative-free optimization, which is doing many forward shots rather than a backward shot, is getting so good that the big divide between gradient-based and non-gradient-based derivative-free optimization, the gap is narrowing more and more, and now they're becoming very, very competitive for complicated problems. So that goes in the same direction as reinforcement learning. Yeah. Yep.
One more, and then I think we will have to go.
If the direct problem is periodic, the way we do this flow simulation is we start with the initial condition and then we do certain numbers of periods until it becomes periodic. But when we go backward in time, do we need to with one periodic one period would it suffice for the joint problem?
Why is the forward problem periodic?
Well, if we deal with a periodic,
is it periodic in time, or is it?
It's periodic in time.
Periodic in time.
So the way we simulate it, usually we start with an initial condition, and then do a certain number of time steps until.
Is it linear in time, or is it linear or nonlinear? If it's
well,
I think in both cases, the time horizon, if it spans more than one period, allows more solutions than the one that is over one period. So if you have a multiple period forward simulation, you also need a multiple period backward simulation with the adjoint. So the adjoint will not give you the right gradient if you sort of cut that one short and only go over one period. It's a little bit like a Floquet analysis where, if you have 5 periods, the amplification over 5 periods is not just 5 times the amplification over one period. There are certain solutions that only grow over 5 periods that are neglected if you only do one period. And it's a little bit like this. Yeah. So the two time horizons have to match.
Okay, so I propose to stop and go to the break. And since we have a very long lunch break, I propose that we shift the next lecture at 11:15. So we recover this 15 minutes, okay? And thanks again to Professor Smith for this excellent lecture. Merci beaucoup. Okay, so welcome back. Now we move to linear dynamical system from Professor Dawson, who you already met, so I'll skip all details and let's go.
Hello, can you hear me up the back? Sort of. I will try to talk loud, and then hopefully we can work it out. Okay, so thanks again for the introduction and for having me back. What, we all good?